it was one of the cases, we're going to call it a special case for lump capacitance, where we looked at this idea that we could have a heat transfer coefficient that varied with the temperature difference between the surface and free stream, and that kind of what describes free convection. Okay. So we did that one, and then we're on to this section that says numerical integration, but I really want to start by setting up this problem. So let me think. First of all, can people hear me and you can see my screen?
Yep.
Yes. Okay. And I forgot to check my pen, and it is not in calibration. Okay. Let me think. You have a homework set due on Wednesday. I've been getting many questions. So it's due on Wednesday. And then you have an exam coming up. So maybe on Wednesday, I'll talk a little bit about the upcoming exam. And hopefully everybody is already planning that it's going to be in person. But this time we'll get a meet at 4 o'clock. It won't be postponed because of the engineering or the week of learning. Okay. So this problem has a 3 millimeter thick panel of aluminum. The properties are given. It's finished on both sides with the treatment that must be cured for 5 minutes above 150 degrees C. The panel is put in an oven with air at 175 degrees C and a convection coefficient of 40 watts per meter squared Kelvin. The oven walls are at 175 degrees C and are large compared to the panel. The emissivity of the panels are 0.8, and the problem statement is then how long do the panels need to be in the oven? All right. If you're thinking through, this has radiation and is not one of our special cases. So we had, convection only. We're in good shape. We had a case with radiation only, which I think is a kind of an exotic case. And then case 3 was pretty all-purpose, but it's one constraint was we couldn't do radiation. And then the 4th case we just talked about was convection only, but with a non-constant heat transfer coefficient. Okay, so this one has radiation, so something a little bit different. I want to draw a picture real quick. So what do we have? Convection going on. They are pretty clear to tell us some things about the oven wall and the emissivity of the plate. So we should be thinking we cannot disregard the radiation. And I'm drawing that this heat transfer occurs on both faces. It's not like one surface is insulated or sitting on a plate, that both are exposed to the convection and radiation. Okay. It's not in the problem statement, so I'm going to make an assumption that we're originally at uniform temperature for this plate. We always make the assumption that we're working with constant properties. Since it's a metal plate and pretty thin, 3 millimeters, I would like to make an estimate of whether lumped capacitance might be valid. So convection and radiation are acting in parallel. And we've done this before, how you add resistances in parallel. But heat transfer coefficient are like conductances. And adding those in parallel, or putting those in parallel is like adding them together. I feel like we've gone through this before. So hopefully it's not too foreign to see that the combination would be the sum of these two heat transfer coefficients. So I'm using this full-blown equation since we know the two extremes of temperature, that the panel starts at 25 degrees C or 298 Kelvin. Okay. And then we know it gets up to at least 150 degrees C. So I'm going to put that one in. So 150 degrees C plus 273 gives me 423 Kelvin. So if we're thinking about, I'm adding the plate temperature to T surroundings, it is the lower temperature, so that when the panel initially goes in, that I see a higher or a smaller effective radiative heat transfer coefficient. So this gives me H rad. Again, if I plug in my numbers, I get a 0.8 here. That was given for the plate. Okay. In this case, when the panel temperature is hotter, okay. So they're not wildly different, but I get 15 watts per meter squared Kelvin. All right. So then if I think through, to check lump capacitance, I want to use the larger of these two heat transfer coefficients to give a good estimate whether lump capacitance could be used.
A quick question.
Yes.
So you still do this step even though we're already assuming that the properties are constant for this problem? You're still doing this just to get the good estimate for the lumped capacitance?
Okay. So lumped capacitance doesn't mean the same thing as constant properties.
Right.
Okay. Yeah. So I'm checking whether, what was I going to say there? I don't remember. So yes, we are going to check, and I'm going to make the claim that that my more constrained case, if it's going to happen at this higher H value, I'm going to be fine. If it's lump capacitance at higher H value, then I'm going to be okay at the lower case. So I'm going to try test with higher H rad. Okay, so maybe I didn't hit your question, but you're willing to have me go on and see if it. Ooh.
I think the confusion was coming from the fact that it's assumed constant properties, yet HRAD appears to be changing, but HRAD isn't so much a material property as it is a derived quantity based off of constant material properties.
Okay. Well
yeah,
said.
I think that's where the confusion was. Yeah,
Okay.
I was equating H rad with K values, which is obviously material property versus the one that changes with temperature here. So
Okay. Okay. So what do I have to do? I really want to put H combined in here. So that's H convection plus H rad, and convection was 40 watts per meter squared Kelvin. Okay. Characteristic length. Our full dimension here is 3 millimeters. But we're cooling it from both faces. So the characteristic length is really going to be half of that distance. And the thermal conductivity given okay, so this is really tiny. Okay. This doesn't mean we can neglect radiation. We still have some other things going on, but what this is telling us is that this thin plate, the temperature distribution, again, if I made this picture, we're adding heat at these surfaces, but the temperature distribution through this is nearly constant. You know, as it heats up, it's not hotter at the surfaces and cooler inside. It's nearly constant. Okay, so I want to write down an energy balance for this system. And we don't have heat leaving the surfaces because both radiation and convection are into the surface. And we don't have volumetric heat generation, but we do have storage. Okay, so if I looked at convection, heat transfer coefficient, surface area, and we're going to assume convection to the surface. So I'm going to put T infinity minus T of our plate surface. And I got two faces that are having heat added. So I'm going to put a 2 out in front for radiation. And I broke this up again. So I'm going to have 2 surfaces. Emissivity, sigma, T surrounding to the 4th, minus T for the plate to the 4th, And then I guess I put the area way back here. We want to get rid of these areas because no information was given on that. So I'm going to divide through by 2A, 2A, and 2A. And I like thinking about volume would be area, whatever my surface area is, times the thickness of the plate. So if I revise this, I'm going to have H T infinity minus T plus emissivity sigma T surroundings to the fourth minus T to the fourth. Oops. And rho L over 2 C sub P, how temperature changes with time. Okay, so this is the equation we want to evaluate. But again, we've talked about this doesn't fit one of our cases for lumped capacitance that we have an analytical solution. But this is where we can come up with a numerical solution, right? So that was the heading before we got to this problem, is that we can make a numerical solution to this. This is our time stepping problems. So I initially know a temperature, right, for this plate. And if I think through, to me, the easiest way, the one I can think through without any numerical methods is, I take an initial temperature here, and I know everything else. I know this heat transfer coefficient. I know T infinity. And this is just convection. I got off my mark for a minute there of thinking about that combined. This is only convection, right? So that's a constant. Emissivity is a constant. The surroundings is a constant. Constant. So I'm going to make a step in time. So I've got this initial temperature. I can solve for dt, this, or change in temperature with time, a single unknown in this equation. And then I use that to calculate a new temperature. And I take a bunch of little tiny time steps. So the first one we're talking about is an explicit method, the one that I just talked about. And it's also called the Euler's method. But let's say our steps will be, for this method, and then I'm going to use this delta T delta T, let's see, is a time step. And then I do this over again. So now I have this new temperature. I plug that back into that equation up above. Okay, and now we're calculating, I don't know what I'm going to do this, a t even newer.
So does
And
the
so I'm-
time step remain the same?
yes, for our purposes. So this is really a pretty brute force. This is not a very elegant method to solve it. But to me, this one's easy to think through. So yes, we're keeping the same time step. We aren't going to do anything. Boy, what do they call that? Where you, well, there are numerical methods where we change the time step, and we aren't going to do that. We're just going to keep chunking through. Okay, so let me make a couple other comments about this. So explicit method, and I don't have a step 3 because we just keep going. Okay. And we'll talk about this graph in just a minute. So explicit method means I can solve everything I need at that current step. It's just a single unknown. And going back to this equation, again, we just have that single unknown there. We can solve for it explicitly.
And is the idea here that you converge just to a temperature after enough time?
Say that again.
Is the idea here that you converge to a temperature after enough time?
For enough time. Okay. Well,
Or maybe I forgot what we were solving for in the first place.
okay. So we're trying to get to,
Oh, I see.
we wanted to find the time.
Right.
And so
okay.
it's not quite converged because the temperature is going to keep going up.
Right.
Okay. But we're going to look for when we finally reach, and I forget what's it, they wanted us to get to 150 degrees. So,
Above,
you know,
above
I
50,
took
yeah.
time steps and I'm looking for when I finally get up to 150 degrees. So it's explicit. Another feature of this Euler's method or this explicit method for setting up this numerical integration. This is a Taylor series expansion again. So we're saying this is my time step. I'm at my new temperature. And it's J plus So if I was looking at my next time step, I take my current temperature, I look at how the temperature is changing with time, and then multiply by my time step. But I can have these higher order terms. Okay, and these are all evaluated at this original time step, time J, or temperature J and TJ. So original time step. And then I could take the third derivative. But in our solution that we looked up above, okay, for how we're solving for that temperature at the next little delta T later, we're only using that first derivative. So we're chopping off all these higher order terms. We talked a little bit about this before, that these higher order terms we're neglecting. And so we say our truncation error for this Euler's method, it's the error is of order delta t squared, because that's the first term we're leaving off.
So this implies if you pick a small enough delta t, that squared value is essentially negligible.
All right, and I feel bad. A plane's going by, and I did not. I can kind of hear you. I couldn't make out what your question was.
I was just saying that implies that if you pick a small enough delta t, because it's squared, it essentially makes the truncation error negligible.
Makes it small enough. Yes, yes. Well, and the other feature is that eventually we're going to look at a way to set up this solution that gets us to a delta t cubed. And then you'd think, well, that's giving me even a smaller truncation error. So people who do numerical methods, these are things they look at. I probably will have you do a simple one of these. And so we won't go into the details of the numerical methods, but this one is delta t squared. And if you could get to a delta t cubed or a delta t to the fourth, that's even better. So there's often more complexity to reduce your truncation error. Okay, but yes, you made a very good point about to reduce our error, we want to pick small delta t's. And we don't have a whole lot of experience in this yet, but yes, smaller delta t's are going to be better. All right, so we talked about explicit. We're talking a little bit about truncation error. And Euler's method is not always stable. Okay, so we know we should be increasing in temperature, right? We're heating the slab of material up. And the solution that I showed has this nice, as I'm taking steps in time, it is moving. I'll scroll up just for a minute. And I only showed only one graph, but it's moving nice, smoothly up to the desired temperature. Okay, but if we picked too large of time steps, we would see something that moves. It's not stable. We'd see, up and down, not a path towards, our final value. Okay. So Euler's method is not stable. You have to pick a delta t that is at least smaller. A rule of thumb is to choose a time step that is smaller than the thermal time constant. All right, here is our, oh, and maybe we put a lump here. I don't quite remember but we used the tau for a thermal time constant. And it was rho volume C sub P over HAS. Okay. And you might be already thinking, we have this combined H of radiation and convection is changing a little bit. Okay, so we could pick the larger heat transfer coefficient to plug into here, and that would give us the smallest lumped the thermal time capacity or thermal time constant, and that might give us a better choice for a delta T. So I plugged in for this problem that we worked. Tau was 66 seconds. Okay. So I would like to use something that is at least smaller than 66 seconds. Okay, but
And you said that the largest H, that's still the combined H that you have there, right?
this would be, yes, the H convection, H rad. Okay. So although I could use something as large as 66 seconds and get a stable solution, it's not going to be very precise because that is a pretty big delta T time step to be taking. So although it's still stable, I still want to consider this idea of taking a small enough delta T that I'm going to get a more accurate answer. Okay, this is a pretty simplified problem. And so we maybe have a little bit more insight of what kind of time steps we can use. But I'm only going to tell you my little story from graduate school. I'm taking a numerical methods class, and I was always bummed out. The teacher would never give us explicit steps for when something was going to be stable. And it was because you can't. There's like a little bit of artistry to developing a stable solution. And it took me quite a while to figure that out. Okay, so I'm finally going back to this graph. Okay. And here is those two go together. I picked a delta T of 15 seconds, so a time step of 15 seconds, and I had to keep stepping through my equation, like, calculating a new temperature with time gradient, calculating a new temperature for the plate, plugging it back into that energy balance equation, keep stepping through. And the time when I hit was 105 seconds. Okay. So then I stepped down my time step to 10 seconds, and now it's 100. The time to reach 150 is 112 seconds. And I kept going down until I got something that reached pretty consistent values. So I'm not changing much as I go to smaller time steps. And I think that is the last case that I put here on the graph, is that I did my smallest time step. That's graphed here, showing our temperature. All right, so we saw this really kind of rough, explicit method for solving for temperature at these different time steps. And this is a numerical integration, and it allows us to handle radiation, which is often the problematic term. Okay, but let's look at one more option.
Is there an error for going too small of a time step?
No, you're asking a very good question. And if I have a chance to look in a book, I will maybe try to come up with something useful to say. So my reason for thinking there could be is I'm thinking about round off error. So if every time you've got round off and you're making all of these steps, that you might cause some issues for too small steps. But that's me thinking off the top of my head, and I don't have a real criteria to give you a guideline or
Okay.
Okay, so the next method is implicit method. So my notes about implicit method. Let's see. So now my equation is going to look like, so I'm shooting to my new temperature, Tj plus 1. So this is my next time step. And it's going to involve the old time step plus the gradient, so how the temperature changes, but for this time step I'm shooting towards. Let's write a few more notes and let me then write down another equation. So this is how we're thinking about how I shoot to my new time step. Before, this gradient was based on my old time step. Now I've moved to the next one. All right. So the benefit, you'll see that this is harder to solve because we're going to have more unknowns. So you cannot explicitly solve. You're going to have, not just a single unknown in your equation. You're going to have multiple unknowns in the equation. But the bonus you get is that this is stable. So you can make your calculations more accurate by choosing a smaller delta, but you're always going to have a stable solution. The truncation error for this one is the same order as the previous one. So we're ignoring any higher order terms again. So no benefit to implicit method to reduce truncation error. Okay, I want to write this out and see if this helps think about how we, set up the implicit method. So for the equation I had, and I'll put some space in here. So for implicit method, if I were solving this equation, each of these places I have a temperature, I'm going to be, it will be written in terms of the unknown temperature at that next time step that we call Tj plus 1. And then this delta, the temperature variation with time, I'm going to write it as a difference between these this new step and the old step. So you see that this unknown Tj plus 1 appears at 3 places in this equation. So it's an implicit solution. And then if I do the explicit, and now I've written the temperature in terms of the current step I'm at, the Tj, where I know it, and I just have my single unknown. So it's, again, it's not always stable, but it's an easier solution to work through.
For the dt component, you have the same formula written for both implicit and explicit. Is that
Yes,
true?
these won't be the same values between these two, but yes.
Okay.
Okay, so I'm back up to this graph that I didn't talk about yet. All right, so I showed 2 different time steps for this solution. And I apologize. I just started looking at this, I don't know, maybe an hour ago. I previously just showed the explicit method. So now I'm showing the implicit method. But if you look, my temperatures are way off. I did this in Kelvin. So let's see, we want to get up to 150 degrees C. So like 423. Ooh, maybe it's even closer. Something out there is a 423. And so it looks so much different than my explicit graph, but it's because I did Kelvin in this one and degrees C in the previous one. All right. What did I have before? 118? Okay. I don't know. It looks like I'm in the ballpark. I can't really. Looks actually a little bit higher. Okay, but in the ballpark. So to solve for the time to reach 423 Kelvin using the implicit method. All right. The last thing I wanted to mention just for a minute. Okay. Has anybody heard of Crank-Nicholson method? No? Okay. So Crank-Nicholson method is really a pretty common method for doing these problems where you are stepping in time. Like you know something at an initial condition and you're stepping in time.
Dr. Brehab,
Yes?
should the temperature and the radiation portion of the equation be T to the 4?
Yes? Sorry? So Crank-Nicholson combines Euler and implicit method. So if we think of Euler as another name for explicit, it combines these two methods. And so if I was going to write the equation, so I'm shooting to this new temperature, Tj plus 1, and it's based on the temperature I'm currently at. But then you use the average of these slopes. So this is the slope I'd get if I looked at the explicit version. This is the slope I'd get if I looked at the implicit solution to the equation. You average those two, so I'm multiplying by the delta t over 2. That seems like a lot more work, but there is a bonus that this is also always stable. So I don't have to pick a certain delta t to keep the solution stable. I likely want to use a small delta t to get some accurate results. And it's hard to show this, so I'm only telling you this, that another bonus that you get from using this method is that you get a truncation error of order delta t cubed. And I always think the fact that you're cubing it maybe makes it seem bigger, but you want to imagine I have a tiny time step, and cubing it is going to give me a smaller truncation error.
Professor,
Yes?
you don't have to go all the way into it, but how do they know that Crank-Nicholson and the implicit method are always stable? Is there like a proof, or did they just kind of test a whole bunch of cases and never found them to be unstable?
All right, you're making me think back. I believe that there is a proof, and I don't know what the proof is. Okay, well, you guys got me on two things. So I don't have a good response. And if I can come up with something in maybe 15 minutes, I will try and talk about that next time. And again, I think there is a proof, and I'm trying to think through. All right, but I'm not going to come up with it for right now, but I will see if I can address it.
Okay. I was just kind of curious which way they went for that one.
Okay, well, to me, it would be interesting if I can come up with a short way to show why it is true. And so in my way of thinking, but I mean, this is very hand wavy, it seems like everything that we do, you know, like to me, implicit is harder than explicit, but you get this bonus that it's stable. And then Crank-Nicholson, it's even more difficult. You're kind of doing two of these things, but the bonus you get now, besides it being stable, it's always you get a smaller truncation error. So heading in the direction of stuff that's always harder, you should get a benefit for it. And I know that doesn't prove why it's stable, but you're hoping you get something for going to a more complicated solution. Okay, we are moving to a new topic. So that took me a while, but that content was all related to lumped capacitance. So we talked about ways we had analytical solutions, and then this last one, which I think is really kind of powerful because we can handle, a wide range of problems now if we're willing to do a numerical solution. Okay. Now we're moving on to 1D transient conduction. Okay, and we're going to jump in. We're going to solve this problem. And people who took heat transfer from U of L, I like doing the hot dog problem. So here it is. It's estimate the time required to cook a hot dog in boiling water. Assume the hot dog is at 6 degrees C. The convective heat transfer coefficient is 100 watts per meter squared Kelvin. And final temperature, we want 80 degrees C at the center line. So, all right, that's not very, it looks like a cylinder, but that's the hot dog. And we got convection occurring. And we got T infinity. Okay, and we know diameter. They don't tell us the length of the hot dog. All right. We're going to assume constant properties, and we're neglecting end effects. So in this section that's one-dimensional transient conduction, we're neglecting end effects because we want to assume we're losing all the heat in the radial direction, so none off of the ends. Okay. Okay. They told us that we put this hot dog in boiling water. So one of the things we need to estimate is T infinity, and we're going to assume we're at sea level so that T infinity for boiling water is going to be 100 degrees C. Okay, so our first thing is we're going to check to see if lumped capacitance is valid. Okay, and you are likely thinking it is not because we just started this new section that says lumped capacitance is like zero-dimensional transient conduction. And now I just put the heading there, one-dimensional. Oh, characteristic length. All right. Hopefully, are you guys getting used characteristic length, volume over surface area. So volume would be pi r squared L, and surface area would be 2 pi r L, right? Okay. And again, we haven't considered heat loss off at these ends, so our surface area is just the cylindrical area. All right, so I want R over 2. So 20 millimeters over 4. And thermal conductivity, so we get a BO number of 1. We cannot use lump capacitance. I am shooting right into this section because I feel you have seen it before. So this is our blow through these, you know, how you do a 1D conduction problem, 1D transient conduction problem. But then I'd like to back up and show you how we get to this first term approximation method that I think you would have used as an undergraduate. Okay, so hopefully this is, you know, maybe not freshly in your mind, but you're kind of vaguely going, oh yeah, I kind of remember that. Okay, so remember we're in chapter 5, and I am just pulling out this equation, and I'll try and explain it, but you may want to do some reading. Theta 0 star. Our book puts a star to say it is a non-dimensional quantity. And the little 0 means it is a center line temperature. So they're using the 0 for center line. Okay. If we expanded this back out, it would be temperature minus T infinity over initial temperature minus T infinity. All right, C and zeta are some coefficients we're going to look up on the next table. Okay, Fourier is a non-dimensional number. I'm putting LC in here for minute because we're going to use Fourier number for walls and then for cylinders and spheres. Okay, but in our case, for this cylinder, LC is going to be the outer radius. So just as a little aside, does anybody remember what units alpha has, thermal diffusivity? Okay, well, we could back it out if we had to, K over rho CCP, but it's got units of meter squared per second. And I like you thinking about, so then when I multiply by time and I divide by a length squared, I get to a unitless quantity. Okay, so this is our first introduction, but we'll see it in a minute again of this Fourier number. Okay. So again, we're supposed to solve for the time for this hot dog to get to an 80 degrees C centerline temperature. So we want to solve for Fourier number because time is embedded in that equation. So
Is there a reason that within Fourier number for characteristic length you said LC equals R naught, but then when we were doing BO number, characteristic length was R over 2?
okay, I'm going to apologize. You probably can't hear it, but a plane went over again. So could you try again and maybe a little bit louder?
Yeah, no worries. I had some confusion where within the Fourier number there, you said that LC, which if I'm not mistaken is characteristic length, is equal to R naught. But then when we were doing the BO number earlier, LC was equal to R over 2. Is that in a different general case or?
Okay. Yes.
Okay.
And I'm only saying that because it's a huge confusion in the other class I teach. We won't be in this section quite as long, but yes. So, okay. So this is our general to use to determine if we can use lumped capacitance. And it ends up giving us a little bit wider range for applying lumped capacitance, which I think you're going to like better. You're going to think, yeah, that's a little bit easier to use. Okay. So it gives us a little bit, but when we start, once we cannot use lumped capacitance and we start using this first term approximation, this chart, so this is 5.1. Oh, and I don't have enough of it. But if you look at the bottom of chart 5.1, it has a note and it says, so it's telling you now to give up that general characteristic length and to use precisely the outer radius to calculate the BO number to look up these C1s and zetas. Okay. So I'm back to this. I want to rearrange to solve for Fourier. So up above, our general rule, we had BO number as 1. But now we're using R0. And so we got a BO number of 2. And I'm going to look up C1 and zeta 1. Oh, I'm not, because it's not on this chart. But this chart keeps going. So I would be looking down this column. And I'm going to find so zeta 1 has units of radians, and C1 is just a constant. I have to use my definition for theta 0 that I wrote earlier. So it's T0, so the center line temperature I want to get to, minus T infinity, divided by initial temperature. And I don't remember talking about that, but in their problem statement, it does say 6 degrees C is initial temperature, and then minus T infinity. And that's over C1. In order to use table 1, this first term approximation, Fourier number has to be greater than 0.2. And when we do a little bit more background, I'll hit that again, because I know I'm just working through this problem. And if you, it's not familiar or not ringing a bell, you're like, where did that come from? But we'll see where it comes from. But a rule is Fourier number has to be greater than 0.2. Okay, so we're good. We got a larger Fourier number. And then we're reminding 0.7188 is alpha T over R0 squared. And we want to solve for T. And I have a side calculation that alpha is K over rho C sub P, and those were given in the problem statement. So alpha is 1.7 times 10 to the minus 7 meters squared per second. So this says that would take 424 seconds or about 7 minutes to heat the hot dog up from the refrigerator to 80 degrees C. Okay, how many people, boy, I won't, I guess I can't get any. I would be interested to know, but I don't know how to get feedback of people who recall doing this solution. And then, and this is how I taught it, using these equations. Did anybody use the Heisler charts?
At least for me personally, none of this is really ringing a bell, but it's been a while.
Okay. All right. So in our book, they don't even use the Heisler charts anymore. They used to be in there, but they're gone. But I do know that some other heat transfer books continue to use Heisler charts, and I was just interested. But we're gonna, these equations aren't too onerous to use. Okay. And all right, we talked about this chart just a minute. It's coefficients for the one term approximation. It has a plane wall geometry, infinite cylinder, which is the one we just did because we said we're neglecting end effects and sphere. Okay, and it really goes farther down, so there's more BO numbers. Oh, and in fact, the bottom is a BO number of infinity. Okay, so all we did was made a run through a problem, and what I'd like to do next time is to set up the governing differential equation, talk about boundary conditions, show you the solution, and it's a separation of variables, but we'll go kind of quick, and then show you what it means, why we just use one term, and why one term is appropriate for certain problems. So hopefully it gives you a little bit more background. Okay, I'm going to end class, but we'll stay on and see if I can address any questions.
I have a quick question, and actually I have two questions. One's related to the test. I was just curious if you know when the end of like the topics are that we're going to be tested on for next Monday.
Okay, and I heard you, but it's funny, a plane came over again. I think because we have so many clouds that they're coming low.
No worries.
okay.
I can repeat it.
No, I did get it. I did get
Okay.
it. Okay. Okay, well, definitely fins, and I think lumped capacitance will be on there, but I'll have to think about precisely where we're ending with lumped capacitance. And I'm trying to think, what else did we do? We did a little bit with two-dimensional conduction. You guys got that shape factor problem that I think nobody's liking, but I thought it was kind of interesting to think about. Okay, does that, I mean, I think it gives you a little bit of an idea. So this next homework set would definitely be the one that you're working on, content to be ready for.
Okay. So I think that ends before chapter 6, right? Am I getting confused?
Yes. So we're still in chapter 5 right now. Yes.
Awesome. Okay. Thank you. And then I think I just had one other question. It was about the homework with the nodal equations problem.
Okay.
For part B, I understand how to kind of set up like the spreadsheet so that it converges and all of that, but I'm getting a little bit confused on how to get that initial guess with the temperatures, because I was looking at an example problem I found in the book, but I think it was like a chapter after the first time we look at nodes. So I'm not sure if it was correct to like kind of like look at, and it looked like they looked at just like conduction. How did they do it? I think they looked at like just heat going into one surface, and then it was just interpreted as that heat then became conduction within that volume. But since we have like that QHT going in node 7, but then we have convection from the top, I wasn't sure how to like kind of go about figuring out the initial temperatures unless I go through each node individually.
Okay. So, and I'm not looking at it now, but the beauty of this should be you could make a guess, and I kind of forget. So what is the convection? Or like, how about free stream temperature?
I think it was 30 degrees.
30 degrees. Okay.
Yeah.
I don't know. I pick 30 degrees. Go ahead and start there.
Okay.
You should get to a solution. If you made a better guess,
yeah,
you're going to converge in fewer iterations.
Gotcha.
But even if you make a bad guess for a two-dimensional steady state, you should get there.
Okay. So that sounds good. Yeah, I was just wondering if there was like an equation for it or if I could just guess, but that sounds perfect. Thank you.
Sure.
Hi, Dr. Briab. I have a question about the homework as well.
Yes.
So for problem 1, the problem statement says to assume that axial conduction is negligible.
Yeah.
Are we assuming that there's no conduction along the length of the slab? Am I interpreting that right? Or is that just in like the Y direction?
Okay, so we got this slab of material and I'm just doing side view. You are saying that there's no conduction. So all we're looking at is the possibility that I have conduction in the X direction because it's one dimensional.
Mm-hmm.
Okay. And then you're ignoring that even. So I think you're going to use the solution that I developed that we went through in class. And that one, we put conduction in, one-dimensional conduction in the X direction, but we then said, well, for most of these problems, the advection is going to be way bigger. So we're dropping it.
Okay. Okay, that makes sense then.
Okay, so again, we started with all three. We had advection, convection off of the surface, and one-dimensional conduction down plus x direction. And then we set up this equation, and we could have done a solution. It's just the one that I picked is pretty practical, and you drop